The camera opens on a vast expanse of grey ocean. Through the morning fog, a colossal container ship cuts silently across the water, its hull etched with rust and responsibility. Every second, somewhere on Earth, another shipment of pork is crossing. A border, skimming across oceans, rumbling down roads. From satellite view, it looks serene, like a slow-moving dot on a logistics dashboard. But zoom in, and you'll find a choreography of pressure gauges, thermal nodes, hydraulic lifts, and nervous systems, both animal and artificial, working in unison. On deck, cold vapor drifts from reinforced containers as cranes lower pallet after pallet into refrigerated holds. Inside, behind sealed doors and data loggers, protein is suspended in time, not frozen, controlled, stabilized with mathematical precision down to the curve of each airflow channel. In the calm silence of the cargo bay, the scene resembles a data center more than a meat locker. But the stakes are biological. If the temperature drops 0.6 degrees too fast, crystallization begins. If the vibration index exceeds tolerance, micro-tears form. And if the torque on the latches is even slightly misaligned, cold leaks, and yield follows. This is the ballet no one sees. A global network that doesn't just move food, it preserves it, with the coordination of a satellite launch and the urgency of a cardiac unit. Because moving 4.9 million tons of pork across continents each year isn't just about trucks or ships. It's about building a thermal, biological, and economic corridor where time, bacteria, and energy are all kept in check by people, machines, and decisions that operate below the surface of public awareness. This is the aquatic highway of nutrition, engineered like a submarine cable system, refined with livestock telemetry, and powered by algorithms trained to predict spoilage before it begins. It doesn't shout, it hums. And in that hum, entire economies breathe. At a glance, pork may not seem like the backbone of a global logistics empire. But in reality, it fuels a trade network worth over $30 billion annually. One that stretches from the intensive production hubs of China and Brazil to the temperature-controlled corridors feeding markets in Europe, Japan, and the Middle East. Behind every shipment is a story of biological constraints, engineering precision, and an invisible clock counting down to degradation. Unlike grains or metals, pork isn't static. It breathes in a way. It reacts to temperature, vibration, and time. Once slaughtered, the biological clock doesn't stop. It accelerates. This makes pork freight one of the most technically demanding forms of protein logistics on the planet. What's being transported isn't a product, but a process frozen in its most fragile state. A metabolic moment stretched across days and thousands of kilometers. To understand the challenge, imagine laying a digital map of pork freight routes over the same infrastructure used in semiconductor shipping or organ transport. That's the level of control required. From abattoir to port, from reefer container to customs checkpoint, each node in the chain must speak the same language of pressure, timing, and thermal behavior. A delay of 5 hours on an airport tarmac in summer, that's not just spoiling. It's a financial hemorrhage. It's a breakdown in the invisible scaffold that holds the cold chain together. And yet, most people have never seen these routes. Never heard of the microfractures that form in polymer insulation due to torque, miscalibration. Never imagined that the airflow inside a container is sculpted. Not simply. This isn't the logistics of the past, with wooden crates and ice blocks. This is agro-industrial choreography, where cargo doesn't just move. It is stabilized, monitored, and guided with the same level of precision used to ship satellites. Pork logistics demand more than refrigeration. They demand fluency in thermodynamics, familiarity with bacterial thresholds, and an engineering mindset capable of treating meat not as matter, but as a living archive of conditions. The market demands tenderness. Technology ensures survival. And the space between the two is where Agroforestry Tech redefines the meaning of transport. Before we move on, Here's something that might catch your interest. If you've ever wondered what kind of tools and innovations make this level of precision possible, not just in theory, but in the real world of ports, farms, and freight corridors, take a moment to check the pinned cut. It's a detail most people overlook, but the kind of detail that keeps everything. The journey begins not at sea or on a highway, but at the processing facility, a space that more closely resembles a clean room than a traditional warehouse. Here, pork is portioned, vacuum-sealed, and prepared with a choreography that follows microbiological time instead of mechanical speed. Every step is calculated, every transition minimized. The goal is simple: reduce the meat's exposure to uncontrolled variables. But in practice, it's a dance of pressure differentials, torque-limited fasteners, and chilling chambers programmed to change temperature in single decimal increments. From this origin point, the cargo moves into pre-cooled containers, not simply boxes, but engineered environments with their own internal intelligence. Each unit is flushed with sterile air, tested for leaks with acoustic sensors, and validated by motion compensation systems designed to counteract the shock. A sudden bump or tilt and stress lines can form along the packaging seals. Even the angle entry, how pallets are slid into place, can influence how vibration travels through the load during transit. It's a mechanical ballet, informed by the same principles used in seeding systems that avoid compacting soil layers in precision agriculture. But not all failures are visible. One of the most damaging threats to pork transport is microfracturing in chilled water conduits, tiny, nearly invisible cracks that form due to improper torque applied during manual containment. These flaws allow condensation to pool unpredictably, disrupting airflow and creating thermal asymmetries inside. The cargo hold, what seems like a minor irregularity on a pressure gauge, can, over time, render tons of meat commercially unviable. To anticipate and neutralize such risks, modern freighters deploy motion sensor grids and intelligent winches that track placement in real time. As each load is secured, its data is synchronized with vessel movement algorithms that predict stress concentrations based on ocean currents, container orientation, and atmospheric fluctuations. It's not just transport, it's prediction layered. The result is a journey where every kilometer is calculated, not just for speed, but for biological preservation. Each reefer box becomes a controlled habitat, and every operation, from forklift to ship hold, functions as part of a larger system. A network where one fluctuation can echo across oceans, and where precision, more than power, is the language that keeps protein alive. Inside a reefer container, temperature is not just a number. It is a terrain, one where gradients must be managed like altitude in an air cabin. Too sudden a drop, and cellular structures in the pork begin to break down, low, and bacterial load outpaces. This is where thermal stress silently undermines yield. A drop of just 0.4 degrees Celsius in less than 3 minutes can raise spoilage rates by over 20%. That difference, invisible to the human eye, translates into millions in economic loss across a single corridor. The core challenge lies in the physiology of pork. Muscle fibers, once metabolically active, retain sensitivity to temperature changes long after slaughter. When defrosting events occur, whether due to mechanical failure, power fluctuation, or improper cycling, these fibers contract unevenly. This creates texture anomalies, moisture loss, and a visible shift in color tone. It's not just quality, it's marketability. And once a batch crosses a sensory threshold, no certificate can reverse the perception of fresh lost. Modern systems fight this decay with sensors, advanced thermodynamic tools that don't just measure ambient temperature, but the heat transfer within the cargo itself. By interpreting metabolic residuals and packaging density, these sensors adjust airflow direction, fan velocity, and even internal wall temperature to maintain equilibrium. It's not chill. The system must adapt, second by second, to the silent respiration of protein. In Norway, one exporter revolutionized its logistics chain by integrating thermal inertia modeling with Internet of Things telemetry. By understanding how heat pulses through densely packed pallets over long distances, they recalibrated their cooling cycles to be anticipatory, active. The result was a savings of over $540,000 annually, not through faster shipping, but smarter control. And the intelligence doesn't sensors. Artificial intelligence now analyzes fish respiration patterns, livestock exhalation models, and protein decay curves to predict spoilage risk per square meter. In refrigerated pork freight, this means learning from biology instead of overriding it. Rather than treating the entire container as a homogeneous volume, AI now differentiates between metric zones, areas of higher heat retention due to packaging density or internal content. Conclusion is simple, yet transformative. Efficiency in meat logistics no longer comes from just insulation, or power. It comes from harmonizing engineering with the biology K. A container is no longer it is a physiological chamber, a mobile biosystem where success is defined not by speed, but by synchronized preservation. Cold chain logistics depends on precision, but even with the most advanced systems, a single manual decision can undo an entire process. This is logistical myopia, when human choices, often well-intended, override sensor data and compromise biological cargo. In one case, a technician paused a thermal cycle based on visual frost buildup. The system had already corrected the imbalance autonomously, but the override created temperature stratification. Within hours, 12% of the pork load had crossed spoilage thresholds. To prevent this, logistics platforms are evolving. Inspired by neuromechanics used in animal modeling, new dashboards guide operators rather than just inform them. They predict the consequences of a command before it's executed, blending instinct with simulation. In fleets using these intelligent aids, freight anomalies have dropped by over 30%. One Chilean vessel, equipped with predictive modeling, rerouted mid-ocean to avoid pressure shifts that had triggered spoilage on previous voyages. The new path preserved 18 tons of turbot without adding time or fuel. Training is evolving too. Staff now use error propagation maps, tools borrowed from aviation, to understand how small deviations expand into systemic loss. The goal is awareness, not blame. Modern cold chains aren't controlled by data alone. They depend on the ability of people and machines to listen to each other and to the cargo. Every correction matters. Every second counts. In a system this sensitive, precision must be shared. Across distant landscapes, fields wake early. Precision sprayers apply nutrients leaf by leaf, while adaptive irrigation systems adjust pressure in response to sunlight and soil moisture. In the cargo holds of ships thousands of kilometers away, another kind of precision unfolds. Containers no longer operate as static, cold boxes. They function as metabolic chambers, tuned to the respiration of protein. The same logic that drives modern agriculture, granular control, adaptive feedback, real-time correction, is reshaping cold chain logistics. Maersk containers, for instance, now use onboard microclimate systems to redistribute cooling power based on the fat content and density of the cargo inside. Each zone is managed individually, much like sectors in a precision-farmed field. The result? Optimized energy use, lower spoilage, and unprecedented cargo fidelity. The redefinition is philosophical as much as technical. A container used to be a passive structure. Now it acts, it senses, it balances itself, and more importantly, it reacts not just to external climate, but to internal biology. Like precision agriculture, this approach rejects uniformity. It sees variation not as a problem, but as data, something to respond to, not suppress. The parallels are striking. Where variable sprayers adjust per leaf, Refrigerated systems now adjust per cut, per pallet, per respiration profile. The cold chain becomes not a corridor, but a living system, one calibrated not only for distance and time, but for the inner rhythm of perishability. If food systems are to remain sustainable, resilient, and scalable, logistics must inherit the intelligence of the farm. The future is not only about moving goods, it's about reading and treating each shipment like a crop with its own biology, its own needs, and its own fragile mission. In the silence of refrigerated holds, beneath layers of sensors, steel, and algorithm, a quiet intelligence pulses. It doesn't seek attention, it sustains. From farm to hull, what moves is more than pork. It's the product of biology guided by engineering, of agriculture extended into the mechanical world. This is the invisible system feeding the planet. A network of machines, minds, and measurements that ensures perishability doesn't become waste, where every decimal matters, where precision isn't luxury, it's survival. Comment 1 if you believe the future of logistics is already but hidden under. And before you go, take a second to check the pinned comment. And you might find something that speaks to you, just as much as the story behind this box.